Hey everyone, and welcome to today's Explainer. Look, if you've ever sat there staring at a computer science textbook, just kind of hoping all those facts will magically stick in your brain, believe me, you are definitely not alone. It happens to the best of us. But today we're going to look at a completely different approach to mastering data representation. We're zeroing in on binary addition and overflow foundations, specifically for your Cambridge IGCSE and O-level exams. We are going to completely transform how you look at this. We're moving past rote memorization, and we're going to figure out exactly what those examiners are actually looking for. Okay, let's dive right into this. It is incredibly easy to view binary addition and overflow as just, well, boring, isolated math facts, right? Just ones and zeros on a page. But I want you to think about an old car odometer for a second. You know, when it hits its absolute maximum mileage and then just suddenly clicks all the way back to zero? Or how about when you're playing a video game and your character suddenly glitches right through a solid wall? So what digital problem does binary addition actually solve here? Why do these things happen? When we start with a realistic scenario like that, these concepts instantly stop being abstract math and they become actual real-world solutions. So here is our roadmap for today's masterclass. We'll start by contextualizing binary concepts. Then we'll build our theoretical foundations, master the technical methodology you need for the exam, walk through the 3-pass revision cycle, and wrap up by learning how to avoid common exam errors. Let's get right to it. Starting off with Section 1, contextualizing binary concepts. And this brilliantly illustrates our first main point. Terminology only really becomes meaningful when we know what practical consequence it has for a user or a system. The exact same binary arithmetic and overflow limits taking place on your exam paper, they are happening right now in smartphones and websites all over the world. If you just memorize that an overflow error happens when an 8-bit binary number exceeds 255, well, you're really only doing half the work. But when you realize that exact same memory error could crash a massive retail database or miscalculate a multi-million-dollar robotic arms movement on an assembly line, suddenly you completely understand the consequence. Remembering the why is the ultimate hack to remembering the what. Moving right along to Section 2, building theoretical foundations. Once we actually understand the context, our baseline knowledge needs to be absolutely rock solid. But here's the secret. True understanding rarely comes from just defining a single term in isolation. Effective study notes have to train you in what we call comparative thinking. Generic memorization is basically just reading a flashcard and hoping it sticks. But let's ask ourselves a comparative question. What exactly is the difference between a simple carry bit in binary addition and an actual overflow error? Well, a carry bit is just normal math, right? You're just carrying a value over to the next column. But an overflow error happens when that carry bit exceeds the total number of bits the computer's processor was built to handle, which causes data loss. If you train your brain to compare and contrast closely related ideas like this right from day one, you will never get confused on exam day. All right, let's look at Section 3, Mastering Technical Methodology. So the crucial point is this. Knowing the theory is one thing, but getting full marks requires a really disciplined path of execution. Top students literally always use this exact 4-step technical methodology. First, you have to identify the exact requirement of the task. Are they asking you to simply add 2 binary bytes together, or do they want you to explain why the result isn't valid? Second, classify the relevant data or hardware involved in the scenario. Third, explain how the process works in a clear, logical sequence that literally anyone could follow. And fourth, and this is a big one, you absolutely must connect your explanation back to the context. Always check the question one last time. Are they looking for causes, effects, advantages, or maybe an evaluation? I want you to pay really close attention to this vital examiner insight. They say students often know the theory but lose marks because they do not anchor their explanation to the details provided. This happens all the time. If an exam question asks you about binary overflow in the specific context of an embedded system or maybe a school network, your answer must stay locked inside that context. Do not just do a generic brain dump of everything you've ever learned about binary addition onto the page. You've got to diagnose the demand correctly, anchor your knowledge to the specific details they gave you, and that is exactly how you secure those higher tier marks. Which brings us to Section 4, the 3-pass revision cycle. So how do we practice this so it just becomes second nature? Let's look at how this builds across your study sessions using the 3-pass strategy. The first pass is all about securing your key definitions and those vital contrasts we talked about earlier. Just get the basics down, like knowing exactly how 1 + 1 = 10 in binary. Simple enough. The second pass is where you rehearse worked explanations, actually draw out the diagrams, and practice your manual binary addition problems. But the third pass is where the magic happens. This pass focuses purely on adaptability. This is where you practice changing the scenario, mixing up similar terms, and forcing yourself to justify your choices. Because computer science exam questions are constantly combining theory with applied, real-world reasoning, this layered progression is absolutely essential for locking in the knowledge. Now for Section 5, Avoiding Common Exam Errors. Listen, knowing what not to do is just as important as knowing what to do. So here is a rapid-fire list of the classic wrong turns that cost students marks every single year. First, using vague wording instead of precise computer science terminology. Second, confusing those similar terms we discussed. Third, missing a critical step in a sequence when you're explaining a binary process. Fourth, failing entirely to answer within the context of the specific scenario given. And here are two of the absolute biggest mistakes: simply naming a device or a method without explaining how it actually works, and giving an advantage but providing zero supporting reason for it. It is so incredibly easy to lose marks by just describing a totally different technology that only sounds kind of related. Now, what's really interesting about this slide is that it provides the ultimate memory test. If you want a perfectly reliable structure to guarantee you know a topic, like binary addition and overflow, inside and out, use these 4 prompts. 1. What is it? 2. How does it work? 3. Where is it used? And 4. Why is it better or worse than an alternative in that specific situation? If you can look away from the screen right now and answer those 4 prompts out loud, clearly and confidently, you are ready for the exam. But hey, if you stumble a bit, don't panic. Just rebuild the topics starting from the key contrast, look at a worked example, and try a scenario-based question again. And that brings us to the core takeaway of today's explainer. We've gone from realistic, real-world hooks all the way through to strict error avoidance. So I'm going to leave you with this challenge. Can you take this concept-first approach and anchor your knowledge perfectly to the context of your very next exam question? Remember, don't just memorize the facts. Understand them, adapt them, and apply them. I really hope this changes how you view your study process, and I absolutely can't wait to explore our next topic with you.